Welcome back, team. In this video, we'll cover everything that you need to know for week 5 of our remote learning. All of the examples that we cover in this video correspond to the particular day of the week that you should be working. So example number 1 corresponds with Monday's work. Example number 2, you guessed it, Tuesday's work. You can pause the video wherever you like. So if you're watching on Monday, you want to pause right after you're done with example number 1 and you want to pick up on Tuesday with example number 2, that's cool. You could also watch the video all the way through multiple times throughout the week so that you are absolutely confident that you are doing the right thing as you're working through your classwork. So let's get started. All right, team, so for example number 1, we have 3 different examples that we'll go over within that example. So might sound confusing, but there are 3 things I want to cover in this first example for you as you get started to work on Monday's classwork. For the first part, we're told to evaluate -4 squared and the difference that is, or what's the difference between -4 squared and in parentheses -4 to the second power. So with -4 squared, when you see the negative on the outside, what that means is that you're going to evaluate what you know 4 squared to be and then place a negative on whatever your product would be. So for example, this would be -16. For this second one, you have -4 in the parentheses, and that's to the power of 2. So you would solve whatever's in the parentheses first, that is -4 times -4. And you know, anytime you multiply a negative times a negative, you're going to get a positive. So that would be +16. So you see that there is a difference between these 2 problems. Whenever there's a negative that exists on the outside of that term, that base, you're going to keep that negative for your final answer. For this last one, we have 3 squared times 3 to the power of 4. And you're asked, what is n? Well, one of your exponent rules that you'll uncover this week states that when you are multiplying terms with the same base, remember that that's your base and that's your exponent. When you're multiplying terms with the same base, you can just add the exponents to get your answer. And so here, in other words, this would be 3 to the power of 6. You could evaluate this and write this 3 times 3, that's 3 to the second power, times, well, what's 3 to the fourth power? That's 3 times 3 times 3 times 3, which 1, 2, 3, 4, 5, 6 is the same as 3 to the power of 6. For Tuesday's work, there's a couple of things or a couple of examples here that would be helpful to you. First is the quotient of powers. Whenever you see the same base being divided, and you have your exponents here, you can subtract those exponents. In other words, when you have the same base that's being divided and you have exponents, this is the same as your base and those exponents being subtracted by numerator minus the denominator. And so what this would be is 3 to the power of 8 minus 2, or 3 to the power of 6. When you have a power of a power, or an example where your exponent has a power or is raised to a power, the rule is here that you are multiplying the exponents. And so here, this is the same as 8 to the power of 2 times 8 to the power of 2 times 8 to the power of 2, or 8 to the power of 6. You're just multiplying 2 and 3 in this example. For example number 3, which corresponds with Wednesday's practice, we're going to deal with some negative exponents. With negative exponents, you could rewrite this to be a to the negative n is equal to, and here's our rule. Whenever we have a negative exponent, what that means is that you want to use the inverse of whatever that base is. And so here we have a to the negative n, and what this is actually a to the positive n underneath a denominator of 1. And so notice that this is the inverse. Remember that in math, if I have a whole number of 7, what's the inverse of 7? It's 1/7. What's the inverse of 2/3? That's right, it's 3/2. And so here, we're taking the idea of that negative being in the exponent. We're keeping the exponent here. We're just making it positive in a new expression, in an equivalent expression. So here we have 3 to the power of negative 2. So what do you think that would be? Yeah, we're going to keep the 3, but now it's going to live underneath the fraction line or the denominator, and that exponent is now positive 2. What about in this example? How is that going to work? Remember that we're taking the inverse of that base, and so what we're going to do is place the 5 over the 2. And this time, instead of it just being negative 6, it's going to be actually positive 6. Our final example here, 1 over 9 to the power of negative 2. What's the inverse of 1/9? It's 9. And instead of there being a negative 2, we now have a positive 2. For example number 4, which corresponds with Thursday's classwork, we have square roots of perfect squares. Now, what's the square root of 25? Remember that squares refer to when you have a base that is multiplied by the base, or you have your base raised to the power of 2. We call that squaring. So like n to the power of 2 would be n times n. So you have to ask yourself what number times itself is going to equal to 25. And so you can go down the line. 1 squared, that's 1 times 1, which is 1. 2 squared, 2 times 2 is 4. 3 squared, get the idea, 3 times 3, that's 9. 4 squared, 4 times 4, that's 16. 5 squared, that's 5 times 5, 25. There you go. So the square root of 25, or what number times itself, is going to be 25. That answer is 5. The square root of perfect squares could also be considered, you could also think about it as you have a square. Now, I realize the irony here, it's called perfect squares, but my drawing is far from perfect. Stop judging me. Find the side length for an area that is 25. And so if you were to count this out, there's 25 perfect squares. In this box, the side length is 5. And remember, that when you're solving for the area, you have to multiply length times width. And so here, you can look at this square that's drawn perfectly here. 5 times 5 would be 25. That's one way to think about the square root of perfect squares. So now it's time for you to practice. Remember that if you have any questions, comments, concerns, you can post a comment in Google Classroom. Thanks so much for watching, and remember, show all your work.